Now we're going to discuss an important and basic concept in statistics, central tendency. This topic will be familiar to many of you from previous classes. You simply may not have realized it was called central tendency. What is central tendency, and why do we want to know the central tendency of a group of scores? Let us first try to answer these questions intuitively. Then we will proceed to a more formal discussion. Imagine this situation. You are in a class with just 4 other students, and the 5 of you took a 5-point pop quiz. Today, your instructor is walking around the room, handing back the quizzes. She stops at your desk and hands you your paper. Written in bold black ink on the front is 3 out of 5. How do you react? Are you happy with your score of 3 or disappointed? How do you decide? You might calculate your percentage correct, realize it is 60%, and be appalled. But it is more likely that when deciding how to react to your performance, you will want additional information. What additional information would you like? If you're like most students, you will immediately ask your neighbors, "What'd you get?" and then ask the instructor, "How did the class do?" In other words, the additional information you want is how your quiz score compares to the other students' scores. You therefore intuitively understand the importance of comparing your score to the class distribution of scores. Should your score of 3 turn out to be among the higher grades, then you'll be pleased after all. On the other hand, if 3 is among the lower scores in the class, you won't be quite so happy. This idea of comparing individual scores to a distribution of scores is fundamental to statistics. So let's explore it further using the same example. The pop quiz you took with your 4 classmates. 3 possible outcomes are shown in this table. They are labeled Dataset A, Dataset B, and Dataset C. Which of the 3 datasets would make you happiest? In other words, in comparing your score with your fellow students' scores, in which dataset would your score of 3 be the most impressive? Take some time to think about your response. In dataset A, everyone's score is 3. This puts your score at the exact center of the distribution. You can draw satisfaction from the fact that you did as well as everyone else. But of course, it cuts both ways. Everyone else did just as well as you. Now consider the possibility that the scores are as described in dataset B. This is a disappointing outcome, even though your score is no different than the one in dataset A. The problem is that the other 4 students had higher grades, putting yours below the center of distribution. When comparing your score to others, you found you had the lowest score of the group. Finally, let's look at dataset C. This is more like it. All of your classmates score lower than you, so your score is above the center of the distribution. Notice that you have the same score of 3 in all the datasets, but the context is different. This is why it is so important to compare your score to the distribution of scores. Now let's change the example in order to develop more insight into the center of a distribution. We'll explore an experiment that looked at chess experience and memory for chess moves. Subjects were shown a chess position and then asked to reconstruct it on an empty chessboard. The number of pieces correctly placed was recorded. This was repeated for 2 more chess positions. The scores represent the total number of chess pieces correctly placed for the 3 chess positions. The maximum possible score was 89. This back-to-back stem and leaf display shows the results of this experiment on memory for chess positions. 2 groups are compared. On the left are the scores of people who don't play chess. On the right are people who play a great deal of chess, tournament players. By comparing the 2 distributions of scores, it is clear that the location of the center of the distribution for the non-players is lower than the center of the distribution for the tournament players. We're sure you get the general idea about the center of a distribution. It's time to move beyond intuition. We need a formal definition of the center of a distribution. In fact, we'll offer you 3 definitions. This is not just generosity on our part. There turn out to be at least 3 different ways of thinking about the center of a distribution, all of them useful in various contexts. In the remainder of this section, we attempt to communicate the idea behind each concept. In the succeeding sections, we will give statistical measures for these concepts of central tendency. Now we explain the three different ways of defining the center of a distribution. All three are called measures of central tendency. One definition of central tendency is the point at which the distribution is in balance. This figure shows the distribution of the five numbers 2, 3, 4, 9, and 15 placed upon a balance scale. If each number weighs 1 pound and is placed at its position along the number line, then it will be possible to balance them by placing a fulcrum at 6.8. For another example, consider the distribution shown in this figure. It is balanced by placing the fulcrum in the middle of the distribution of scores. This figure illustrates that the same distribution cannot be balanced by placing the fulcrum to the left of center. This figure shows an asymmetric distribution. To balance it, we cannot put the fulcrum halfway between the lowest and highest values. Placing the fulcrum at the halfway point would cause it to tip towards the left. The balance point defines one sense of a distribution center. Another way to define the center of a distribution is based on the concept of the sum of the absolute differences. Consider the distribution made up of the five numbers 2, 3, 4, 9, and 16. Let's see how far the distribution is from 10, picking a number arbitrarily. This table shows the sum of the absolute differences of these numbers from the number 10. The first row of the table shows that the absolute value of the difference between 2 and 10 is 8. The second row shows that the difference between 3 and 10 is 7, and similarly for the other rows. When we add up the five absolute differences, we get 28. So the sum of the absolute differences from 10 is 28. Likewise, the sum of the absolute differences from 5 equals 3 plus 2 plus 1 plus 4 plus 11, which equals 21. So the sum of the absolute differences from 5 is smaller than the sum of the absolute differences from 10. In this sense, 5 is closer overall to the other numbers than is 10. We are now in position to define a second way of measuring central tendency, this time in terms of absolute differences. Specifically, according to our second definition, the center of a distribution is the number for which the sum of the absolute differences is smallest. As we just saw, the sum of the absolute differences from 10 is 28, and the sum of the absolute differences from 5 is 21. It turns out that the value for which the sum of absolute differences is smallest is 4, for which the sum of absolute differences is 20. In a later section, we will show how to find the value for which the sum of the absolute differences is smallest. We now discuss one more way to define the center of a distribution. It is based on the concept of the sum of squared differences. Again, consider the distribution of the five numbers 2, 3, 4, 9, and 16. This table shows the sum of the squared differences of these numbers from the number 10. The first row in the table shows that the squared value of the difference between 2 and 10 is 8 squared, which equals 64. The second row shows that the squared difference between 3 and 10 is 49, and so forth. When we add up all these differences, we get 486. Changing the target from 10 to 5, we calculate the sum of the squared differences from 5 as 9 plus 4 plus 1 plus 16 plus 121, which equals 151. So the sum of the squared differences from 5 is smaller than the sum of the squared differences from 10. Is there a value for which the sum of the squared differences is even smaller than 151? Yes, it is possible to reach 134.8. Can you find the target number for which the sum of squared deviations is 134.8? it can be challenging to find the value that minimizes this sum. We'll show you how to do it in a later section.